Chapter 9? Electricity. In 1900 the real nature of electricity appears to be as unknown as it was in 1800. Franklin in the 18th century defined electricity as consisting of particles of matter incomparably more subtle than air, and which pervaded all bodies. At the close of the 19th century, electricity defined as simply a form of energy which imparts to material substances a peculiar state or condition, and that all such substances partake more or less of this condition. These theories and the late discovery of Hertz that electrical energy manifests itself in the form of waves, oscillations or vibrations, similar to light, but not so rapid as the vibrations of light, constitute about all that is known about the nature of this force. Franklin believed it was a single fluid, but others taught that there were two kinds of electricity, positive and negative, that the like kinds were repulsive and the unlike kinds attractive, and that when generated it flowed in currents. Such terms are not now regarded as representing actual varieties of this force, but are retained as convenient modes of expression, for want of better ones, as expressing the conditions or states of electricity when produced. Electricity produced by friction, that is, developed upon the surface of a body by rubbing it with a dissimilar body, and called frictional or static electricity, was the only kind produced artificially in the days of Franklin. What is known as galvanism, or animal electricity, also takes its date in the 18th century, to which further reference will be made. Since 1799 there have been discovered additional sources, among which are voltaic electricity, or electricity produced by chemical action, such as is manifested when two dissimilar metals are brought near each other or together, and electrical manifestations produced by a decomposing action, one upon the other through a suitable medium, inductive electricity, or electricity developed or induced in one body by its proximity to another body through which a current is flowing, magnetic electricity. The conversion of the power of a magnet into electric force, and the reverse of this, the production of magnetic force by a current of electricity, and thermal electricity, or that generated by heat. Electricity developed by these, or other means in contradistinction to that produced by friction, has been called dynamic, but all electric force is now regarded as dynamic, in the sense that forces are always in motion and never at rest. Many of the manifestations and experiments in later-day fields which, by reason of their production by different means, have been given the names of discovery and invention, had become known to Franklin and others, by means of the old methods in frictional electricity. They are all, however, but different routes leading to the same goal. In the midst of the brilliant discoveries of modern times confronting us on every side, we should not forget the honorable efforts of the fathers of the science. We need not dwell on what the ancients produced in this line. It was a single fact only: the Greeks discovered that amber, a resinous substance, when rubbed would attract lighter bodies to it. In 1600 appeared the father of modern electricity, Dr. Gilbert of Colchester, physician to Queen Elizabeth. He revived the one experiment of antiquity, and added to it the further fact that many substances besides amber, when rubbed, would manifest the same electric condition, such as sulfur, sapphire, wax, glass and other bodies. And thus he opened the field of electrodes. He was the first to use the terms, electricity, electric and electrode, which he derived from the word electron, the Greek name for amber. He observed the actions of magnets, and conjectured the fundamental identity of magnetism and electricity. He arranged an electrometer, consisting of an iron needle poised on a pivot, by which to note the action of the magnet. This was about the time that Otto von Guericke of Magdeburg, Germany, was born. He became a natural philosopher, and for 35 years was burgomaster of his native town. He invented the air pump, and he it was who illustrated the force of atmospheric pressure by fitting together two hollow brass hemispheres which, after the air within them had been exhausted, could not be pulled apart. He also invented a barometer, and as an astronomer suggested that the return of comets might be calculated. He invented and constructed the first machine for generating electricity. It consisted of a ball of sulfur rotated on an axis, and which was electrified by friction of the hand, the ball receiving negative electricity while the positive flowed through the person to the earth. With this machine he heard the first sound and saw the first light in artificially excited electricity. The machine was improved by Sir Isaac Newton and others, and before the close of that century was put into substantially its present form of a round glass plate rotated between insulated leather cushions coated with an amalgam of tin and zinc, the positive or vitreous electricity thus developed being accumulated on two large hollow brass cylinders with globular ends, supported on glass pillars. Gray in 1729 discovered the conductive power of certain substances, and that the electrical influence could be conveyed to a distance by means of an insulated wire. This was the first step towards the electric telegraph. Dufay, the French philosopher and author, who in 1733 to 1737 wrote the Memoirs of the French Academy, was, it seems, the first to observe electrical attractions and repulsions, that electrified resinous substances repelled like substances while they attracted bodies electrified by contact with glass, and he therefore, to the latter applied the term vitreous electricity and to the former the term resinous electricity. In 1745 Professor Muschenbroek of Leiden University developed the celebrated Leiden Jar. This is a glass jar coated both inside and outside with tinfoil for about 4/5 of its height. Its mouth is closed with a cork through which is passed a metallic rod, terminating above in a knob and connected below with the inner coating by a chain or a piece of tinfoil. If the inner coating be connected with an electrical machine and the outer coating with the earth, a current of electricity is established, and the inner coating receives what is called a positive, and the outer coating a negative charge. On connecting the two surfaces by means of a metallic discharger having a non-conducting handle, a spark is obtained. Thus the Leiden jar is both a collector and a condenser of electricity. On arranging a series of such jars and joining their outer and inner surfaces, and connecting the series with an electrical machine, a battery is obtained of greater or less power according to the number of jars employed and the extent of supply from the machine. The principle of the Leiden jar was discovered by accident. Cuneus, a pupil of Muschenbroek, was one day trying to charge some water in a glass bottle with electricity by connecting it with a chain to the sparking knob of an electrical machine. Holding the bottle in one hand, he arranged the chain with the other, and received a violent shock. His teacher then tried the experiment himself, with a still livelier and more convincing result, whereupon he declared that he would not repeat the trial for the whole kingdom of France. When the science of static electricity was thus far developed, with a machine for generating it and a collector to receive it, many experiments followed. Charles Morrison in 1753, in the Scots Magazine, proposed a telegraph system of insulated wires with a corresponding number of characters to be signalled between two stations. Other schemes were proposed at different times down to the close of the century. Franklin records among several other experiments with frictional electricity accumulated by the Leiden jar battery the following results, produced chiefly by himself: the existence of an attractive and a repulsive action of electricity, the restoration of the equilibrium of electrical force between electrified and non-electrified bodies, or between bodies differently supplied with the force, the electroscope. A body charged with electricity and used to indicate the presence and condition of electricity in another body, the production of work, as the turning of wheels, by which it was proposed a spit for roasting meat might be formed, and the ringing of chimes by a wheel, which was done, the firing of gunpowder, the firing of wood, resin and spirits, the drawing off a charge from electrified bodies at a near distance by pointed rods, the heating and melting of metals, the production of light, the magnetizing of needles and of bars of iron, giving rise to the analogy of magnetism, and electricity. Franklin, who had gone thus far, and who also had drawn the lightning from the clouds, identified it as electricity, and taught the mode of its subjection, felt chagrined that more had not been done with this subtle agent in the service of man. He believed, however, that the dayspring of science was opening, and he seemed to have caught some reflection of its coming light. Observing the return to life and activity of some flies long imprisoned in a bottle of Madeira wine and which he restored by exposure to the sun and air, he wrote that he should like to be immersed at death with a few friends in a cask of Madeira, to be recalled to life 100 years thence to observe the state of his country. It would not have been necessary for him to have been embalmed that length of time to have witnessed some great developments of his favourite science. He died in 1790, and it has been said that there was more real progress in this science in the first decade of the 19th century than in all previous centuries put together. Before opening the door of the 19th century, let us glance at one more experiment in the 18th. While the aged Franklin was dying, Dr. Luigi Golvani of Bologna, an Italian physician, medical lecturer, and learned author, was preparing for publication his celebrated work, De Viribus Electricitatis in Motu Musculari Commentrius, in which he described his discovery made a few years before of the action of the electric current on the legs and spinal column of a frog hung on a copper nail. This discovery at once excited the attention of scientists, but in the absence of any immediate practical results the multitude dubbed him the Frog Philosopher. He proceeded with his experiments on animals and animal matter, and developed the doctrine and theories of what is known as animal or galvanic electricity. His fellow countryman, and contemporary, Professor Volta of Pavia, took decided issue with Galvani and maintained that the pretended animal electricity was nothing but electricity developed by the contact of two different metals. Subsequent investigations and discoveries have established the fact that both theories have truth for their basis, and that electricity is developed both by muscular and nervous energy as well as by chemical action. In 1799 Volta invented his celebrated pile, consisting of alternate discs of copper and zinc separated by a cloth moistened with a dilute acid, and soon after an arrangement of cups, each containing a dilute acid and a copper and a zinc plate placed a little distance apart, and thus dispensing with the cloth. In both instances he connected the end plate of one kind with the opposite end plate of the other kind by a wire, and in both arrangements produced a current of electricity. To the discoveries, experiments, and disputes of Golvani and Volta, and to those of their respective adherents, the way was opened to the splendid electrical inventions of the century, and the discovery of a new world of light, heat, speech and power. The discoveries of Golvani and Volta at once set leading scientists at work. Fabroni of Florence, and Sir Humphry Davy and Wollaston of England, commenced interesting experiments, showing that rapid oxidation and chemical decomposition of the metals took place in the voltaic pile. By the discoveries of Golvani the physicians and physiologists were greatly excited, and believed that by this new vital power the nature of all kinds of nervous diseases could be explored and the remedy applied. Volta's discovery excited the chemists. If two dissimilar metals could be decomposed and power at the same time produced, they contended that practical work might be done with the force. In 1800 Nicholson and Carlisle decomposed water by passing the electric current through the same, Ritter decomposed copper sulfate, and Davy decomposed the alkalis, potash and soda. Thus the art of electrolysis, the decomposition of substances by the galvanic current, was established. Later Faraday laid down its laws. Naturally inventions sprung up in new forms of batteries. The pile and cup battery of Volta had been succeeded by the Trough Battery, a long box filled with separated plates set in dilute acid. The Trough Battery was used by Sir Humphry Davy in his series of great experiments, 1806 to 1808, in which he isolated the metallic bases, calcium, sodium, potassium, etc. It consisted of 2,000 double plates of copper and zinc, each having a surface of 32 square inches. With this same Trough Battery Davy in 1812 produced the first electric carbon light, the bright herald of later glories. Among the most noted new batteries were Daniels, Groves and Bunson's. They are called the two-fluid batteries, because in place of a single acidulated bath in which the dissimilar metals were before placed, two different liquid solutions were employed. John Frederick Daniel of London, noted for his great work, meteorological essays, and other scientific publications, and as Professor of Chemistry in King's College, in 1836, described how a powerful and constant current of electricity may be continued for an unlimited period by a battery composed of zinc standing in an acid solution and a sheet of copper in a solution of sulfate of copper. Sir William Robert Grove, first an English physician, then an eminent lawyer, and then a professor of natural philosophy, and the first to announce the great theory of the correlation of physical forces, in 1839 produced his battery, much more powerful than any previous one, and still in general use. In it zinc and platinum are the metals used, the zinc bent into cylindrical form and placed in a glass jar containing a weak solution of sulfuric acid, while the platinum stands in a porous jar holding strong nitric acid and surrounded by the zinc. Among the electrical discoveries of Grove were the decomposition by electricity of water into free oxygen and hydrogen, the electricity of the flame of the blowpipe, electrical action produced by proximity, without contact, of dissimilar metals, molecular movements induced in metals by the electric current, and the conversion of electricity into mechanical force. Robert Wilhelm Bunsen, a German chemist and philosopher and scientific writer, who invented some of the most important aids to scientific research of the century, who constructed the best working chemical laboratory on the continent and founded the most celebrated schools of chemistry in Europe, invented a battery, sometimes called the carbon battery, in which the expensive pole of platinum, in the Grove battery, is replaced by one of carbon. It was found that this combination gave a greater current than that of zinc and platinum. A great variety of useful voltaic batteries have since been devised by others, too numerous to be mentioned here. There is another form of battery having for its object the storing of energy by electrolysis, and liberating it when desired, in the form of an electric current, and known as an accumulator, or secondary, polarization, or storage battery. Professor Ritter had noticed that the two plates of metal which furnished the electric current, when placed in the acid liquid and united, could in themselves furnish a current, and the inventing of storage batteries was thus produced. The principal ones of this class are Gustav Plant's of 1860 and M. Camille Fauray's of 1880. These have still further been improved. Still another form are the thermoelectric batteries, in which the electromotive force is produced by the joining of two different metals, connecting them by a wire and heating their junctions. Thus, an electric current is obtained directly from heat, without going through the intermediate processes of boiling water to produce steam, using this steam to drive an engine, and using this engine to turn a dynamo machine to produce power. But let us retrace our steps, as previously stated. Franklin had experimented with frictional electricity on needles, and had magnetized and polarized them and noticed their deflection, and Lesage had established an experimental telegraph at Geneva by the same kind of electricity more than 100 years ago. But frictional electricity could not be transmitted with power over long distances, and was for practical purposes uncontrollable by reason of its great diffusion over surfaces, while voltaic electricity was found to be more intense and could be developed with great power along a wire for any distance. Fine wires had been heated and even melted by Franklin by frictional electricity, and now Ritter, Paff and others observed the same effect produced on the conducting wires by a voltaic current, and Curtet, on closing the passage with a piece of charcoal, produced a brilliant light, which was followed by Davy's light already mentioned. As early as 1802 an Italian savant, Gian di Romagnosi of Trent, learning of Volta's discovery, observed and announced in a public print the deflection of the magnetic needle when placed near a parallel conductor of the galvanic current. In the years 1819 and 1820 so many brilliant discoveries and inventions were made by eminent men, independently and together, and at such near and distant places, that it is hard telling who and which was first. It was in 1819 that the celebrated Danish physicist, Ørsted of Copenhagen, rediscovered the phenomena that the voltaic current would deflect a magnetic needle, and that the needle would turn at right angles to the wire. In 1820 Professor S.C. Schweiger of Halle discovered that this deflecting force was increased when the wire was wound several times round the needle, and thus he invented the magnetizing helix. He also then invented a galvanomagnetic indicator, a single-wire circuit, by giving the insulated wire a number of turns around an elongated frame longitudinally enclosing the compass needle, thus multiplying the effect of the current upon the sensitive needle, and converting it into a practical measuring instrument, known as the galvanometer, and used to observe the strength of currents. In the same year Arago found that iron filings were attracted by a voltaic charged wire, and Arago and Davy that a piece of soft iron surrounded spirally by a wire through which such a current was passed would become magnetic, attract to it other metals while in that condition, immediately drop them the instant the current ceased, and that such current would permanently magnetize a steel bar. The elements of the electromagnet had thus been produced. It was in that year that Ampere discovered that magnetism is the circulation of currents of electricity at right angles to the axis of the needle or bar joining the two poles of the magnet. He then laid down the laws of interaction between magnets and electrical currents, and in this same year he proposed an electric magneto-telegraph consisting of the combination of a voltaic battery, conducting wires, and magnetic needles, one needle for each letter of the alphabet. The discoveries of Ampere as to the laws of electricity have been likened to the discovery of Newton of the law of gravitation. Still no practical result, that is, no useful machine, had been produced by the electromagnet. In 1825 Sturgeon of England bent a piece of wire into the shape of a horseshoe, insulated it with a coating of sealing wax, wound a fine copper wire around it, thus making a helix, passed a galvanic current through the helix, and thus invented the first practical electromagnet. But Sturgeon's magnet was weak, and could not transmit power for more than 50 feet. Already, however, it had been urged that Sturgeon's magnet could be used for telegraphic purposes, and a futile trial was made. In the field, during this decade also labored the German professors Gauss and Weber, and Baron Schilling of Russia. In 1829 Professor Barlow of England published an article in which he summarized what had been done, and scientifically demonstrated to his own satisfaction that an electromagnetic telegraph was impracticable, and his conclusion was accepted by the scientific world as a fact. This was, however, not the first nor the last time that scientific men had predicted impracticabilities with electricity which afterwards blossomed into full success. But even before Professor Barlow was thus arriving at his discouraging conclusion, Professor Joseph Henry at the Albany Institute in the state of New York had commenced experiments which resulted in the complete and successful demonstration of the power of electromagnetism for not only telegraph purposes but for almost every advancement that has since been had in this branch of physics. In March 1829 he exhibited at his institute the magnetic spool or bobbin, that form of coil composed of tightly wound, silk-covered wire which he had constructed, and which since has been universally employed for nearly every application of electromagnetism, of induction, or of magneto-electrics. And in the same year and in 1830 he produced those powerful magnets through which the energy of a galvanic battery was used to lift hundreds of tons of weight. In view of all the facts now historically established, there can be no doubt that previous to Henry's experiments the means for developing magnetism in soft iron were imperfectly understood, and that, as found by Professor Barlow, the electromagnet which then existed was inapplicable and impracticable for the transmission of power to a distance. Professor Henry was the first to prove that a galvanic battery of intensity must be employed to project the current through a long conductor, and that a magnet of one long wire must be used to receive this current, the first to magnetize a piece of soft iron at a distance and call attention to its applicability to the telegraph, the first to actually sound a bell at a distance by means of the electromagnet. And the first to show that the principles he developed were applicable and necessary to the practical operation of an effective telegraph system. Sturgeon, the parent of the electromagnet, on learning of Henry's discoveries and inventions, wrote, "Professor Henry has been enabled to produce a magnetic force which totally eclipses every other in the whole annals of magnetism, and no parallel is to be found since the miraculous suspension of the celebrated Oriental impostor in his iron coffin." Philosophical Magazine and Annals, 1832. The third decade was now prepared for the development of the telegraph. As to the telegraph in its broadest sense, as a means for conveying intelligence to a distance quickly and without a messenger, successful experiments of that kind have existed from the earliest times, from the signal fires of the ancients. From the flag signals between ships at sea, introduced in the 17th century by the Duke of York, then Admiral of the English fleet, and afterwards James II of England, from the semaphore telegraph of M. Chap, adopted by the French government in 1794, consisting of bars pivoted to an upright stationary post, and made to swing vertically or horizontally to indicate certain signals, and from many other forms of earlier and later days. As to electricity as an agent for the transmission of signals, the idea dates, as already stated, from the discovery of Stephen Gray in 1729, that the electrical influence could be conveyed to a distance by the means of an insulated wire. This was followed by the practical suggestions of Franklin and others. But when, as we have seen, voltaic electricity entered the field, electricity became a more powerful and tractable servant, and distant intelligent signals became one of its first labors. The second decade was also made notable by the discovery and establishment by George Simon Ohm, a German professor of physics, of the fundamental mathematical law of electricity. It has been expressed in the following terms: A. The current strength is equal to the electromotive force divided by the resistance. B. The force is equal to the current strength multiplied by the resistance. C. The resistance is equal to the force divided by the current strength. The historical development and evolution of the telegraph may be now summarized. 1. The discovery of galvanic electricity by Golvani, 1786 to 1790. 2. The galvanic or voltaic battery by Volta in 1800. 3. The galvanic influence on a magnetic needle by Romagnosi, 1802, Ørsted, 1820. 4. The Galvanometer of Schweiger, 1820, the parent of the needle system. 5. The electromagnet by Arago and Sturgeon, 1820 to 1825, the parent of the magnet system. Then followed in the third decade the important series of steps in the evolution, consisting of: first, and most vital, Henry's discovery in 1829 and 1830 of the intensity or spool wound magnet, and its intimate relation to the intensity battery, and the subordinate use of an armature as the signaling device. Second, Gauss's improvement in 1833, or probably Schilling's considerably earlier, of reducing the electric conductors to a single circuit by the ingenious use of a dual sign so combined as to produce a true alphabet. Third, Weber's discovery in 1833 that the conducting wires of an electric telegraph could be efficiently carried through the air without any insulation except at their points of support. Fourth, Daniel's invention of a constant galvanic battery in 1836. Fifth, Steinheil's remarkable discovery in 1837 that the Earth may form the returning half of a closed galvanic circuit, so that a single conducting wire is sufficient for all telegraphic purposes. Sixth, Morse's adaptation of the armature and electromagnet of Henry as a recording instrument in 1837 in connection with his improvement in 1838 on the Schilling, Gauss and Steinheil alphabets by employing the simple dot and dash alphabet in a single line. He was also assisted by the suggestions of Profs. Dana and Gale, to which must be added his adoption of Alfred Vail's improved alphabet, and Vail's practical suggestions in respect to the recording and other instrumentalities. To these should be added the efforts in England, made almost simultaneously with those of Morse, of Wheatstone and Cook and Davy, who were reaching the same goal by somewhat different routes. Morse in 1837 commenced to put the results of his experiments and investigations in the form of caveats, applications and letters patent in the United States and in Europe. He struggled hard against indifference and poverty to introduce his invention to the world. It was not until 1844 that he reduced it to a commercial practical success. He then laid a telegraph from Washington to Baltimore under the auspices of the United States government, which after long hesitation appropriated $30,000 for the purpose. It was on the 24th day of May, 1844, that the first formal message was transmitted on this line between the two cities and recorded by the electromagnet in the dot and dash alphabet, and this was immediately followed by other messages on the same line. Morse gathered freely from all sources of which he could avail himself knowledge of what had gone before. He was not a scientific discoverer, but an inventor, who, adding a few ideas of his own to what had before been discovered, was the first to combine them in a practical useful device. What he did as an inventor, and what anyone may do to constitute himself an inventor, by giving to the world a device which is useful in the daily work of mankind, as distinguished from the scientific discoverer who stops short of successful industrial work, is thus stated by the United States Supreme Court in an opinion sustaining the validity of his patents, after all the previous art had been produced before it. Neither can the inquiries he made nor the information or advice he received from men of science in the course of his researches impair his right to the character of an inventor. No invention can possibly be made, consisting of a combination of different elements of power, without a thorough knowledge of the properties of each of them, and the mode in which they operate on each other. And it can make no difference in this respect, whether he derives his information from books, or from conversation with men skilled in the science. If it were otherwise, no patent in which a combination of different elements is used would ever be obtained, for no man ever made such an invention without having first obtained this information, unless it was discovered by some fortunate accident. And it is evident that such an invention as the electromagnetic telegraph could never have been brought into action without it, for a very high degree of scientific knowledge and the nicest skill in the mechanic arts are combined in it, and were both necessary to bring it into successful operation. The fact that Morse sought and obtained the necessary information and counsel from the best sources, and acted upon it, neither impairs his rights as an inventor nor detracts from his merits. O'Reilly vs. Morse, 5 Howard. The combination constituting Morse's invention comprised a main wire circuit to transmit the current through its whole length whenever closed, a main galvanic battery to supply the current, operating keys to break and close the main circuit, office circuits, a circuit of conductors and batteries at each office to record the message there, receiving spring lever magnets to close an office circuit when a current passes through the main circuit, adjusting screws to vary the force of the main current, marking apparatus, consisting of pointed pieces of wire, to indent dots and lines upon paper, clockwork to move the paper indented, and magnet sounders to develop the power of the pointer and of the armatures to produce audible distinguishable sounds. It was soon learned by operators how to distinguish the signs or letters sent by the length of the click of the armature, and by thus reading by sound the reading of the signs on paper was dispensed with, and the device became an electric magnetic acoustic telegraph. What is known as the Morse system has been improved, but its fundamental principles remain, and their worldwide use constitutes still the daily evidence of the immense value of the invention to mankind. Before the 1844 reduction to practice, Morse had originated and laid the first submarine telegraph. This was in New York Harbor in 1842. In a letter to the Secretary of the United States Treasury, August 10, 1843, he also suggested the project of an Atlantic telegraph. While Henry was busy with his great magnets and Morse struggling to introduce his telegraph, Michael Faraday was making those investigations and discoveries which were to result in the application of electricity to the service of man in still wider and grander fields. Faraday was a chemist, and Davy's most brilliant pupil and efficient assistant. His earliest experiments were in the line of electrolysis. This was about 1822, but it was not until 1831 that he began to devote his brilliant talents as an experimentalist and lecturer wholly to electrical researches, and for a quarter of a century his patient, wonderful labors and discoveries continued. It has been said that although Ørsted was the discoverer of electromagnetism, and Ampere its expounder, Faraday made the science of magnets electrically what it is at the present day. Great magnetic power having been developed by passing a galvanic current around a bar of soft iron, Faraday concluded that it was reasonable to suppose that as mechanical action is accompanied by an equal amount of reaction, electricity ought to be evolved from magnetism. It was in 1831 that Faraday demonstrated before the Royal Society that if a magnetized bar of steel be introduced into the center of a helix of insulated wire, there is at the moment of introduction of the magnet a current of electricity set up in a certain direction in the insulated wire forming the helix, while on the withdrawal of the magnet from the helix a current in an opposite direction takes place. He also discovered that the same phenomenon was to be observed if for the magnet was substituted a coil of insulated wire, through which the current from a voltaic element was passing, and further that when an insulated coil of wire was made to revolve before the poles of a permanent magnet, electric currents were induced in the wires of the coil. Journal of the Society of Arts. On these discoveries were based the action of all Magneto-Dynamo-Electric Machines, machines that have enabled the world to convert the energy of a steam engine in its stall, or a distant waterfall, into electric energy for the performance of the Herculean labors of lighting a great city, or an ocean-bound lighthouse, or transporting quickly heavy loads of people or freight up and down and to and fro upon the earth. As before stated, Faraday was also the first to proclaim the laws of electrolysis, or electrochemical decomposition. He expressed conviction that the forces termed chemical affinity and electricity are one and the same. Subsequently the great Helmholtz, having proved by experiment that in the phenomena of electrolysis no other force acts but the mutual attractions of the atomic electric charges, came to the conclusion that the very mightiest among the chemical forces are of electric origin. Faraday having demonstrated by his experiments that chemical decomposition, electricity, magnetism, heat and light, are all interconvertible and correlated forces, the inventors of the age were now ready to step forward and put these theories at work in machines in the service of man. Faraday was a leader in the field of discovery. He left to inventors the practical application of his discoveries. Professor Henry in America was, contemporaneously with Faraday, developing electricity by means of magnetic induction. In 1832, Pixii, a philosophical instrument maker of Paris, and Joseph Saxton, an American then residing in London, invented and constructed Magneto Machines on Faraday's principle of rendering magnetic a core of soft iron surrounded with insulated wire from a permanent magnet, and rapidly reversing its polarity, which machines were used to produce sparks, decompose liquids and metals, and fire combustible bodies. Saxton's machine was the well-known electric shock machine operated by turning a crank. A similar device is now used for ringing telephone call bells. Professor C.G. Page of Washington and Roonhof of Paris each made a machine, well known as the Roonhof Coil, by which intense electromagnetic currents by induction were produced. The production of electrical illumination was now talked of more than ever. Scientists and inventors now had two forms of electrical machines to produce light, the Voltaic Battery and the Magneto-Electric apparatus. But a period of comparative rest took place in this line until 1850, when Professor Nollet of Brussels made an effort to produce a powerful magneto-electric machine for decomposing water into its elements of hydrogen and oxygen, which gases were then to be used in producing the limelight, and a company known as the Alliance was organized at Paris to make large machines for the production of light. We have seen that Davy produced a brilliant electric light with two pieces of charcoal in the electric circuit of a voltaic battery. Greener and State revived this idea in a patent in 1845. Shortly after Nolet's machine, F.H. Holmes of England improved it and applied the current directly to the production of electric light between carbon points. And Holmes and Faraday in 1857 prepared this machine for use. On the evening of December 8, 1858, the first practical electric light, the work of Faraday and Holmes, flashed over the troubled sea from the South Foreland lighthouse. On June 6, 1862, this light was also introduced into the lighthouse at Dungeness, England. The same light was introduced in French lighthouses in December, 1863, and also in the work on the docks of Cherbourg. At this time Germany was also awake to the importance of this invention, and Dr. Werner Siemens of Berlin was at work developing a machine for the purpose into one of less cost and of greater use. Inventors were not yet satisfied with the power developed from either the Voltaic Battery or the Magneto-Electric Machine, and continued to improve the latter. In 1867, the same year that Faraday died, and too late for him to witness its glory, came out the most powerful Magneto-Electric Machine that had yet been produced. It was invented by Wilde of London, and consisted of very large electromagnets, or field magnets, receiving their electric power from the lines of force discovered by Faraday, radiating from the poles of a soft iron magnet, combined with a small magneto-electric machine having permanent magnets, and by which the current developed in the smaller machine was sent through the coils of the larger magnets. By this method the magnetic force was vastly multiplied, and electricity was produced in such abundance as to fuse thick iron wire 15 inches long and 1/4 of an inch in diameter, and to develop a magnificent arc light. Quickly succeeding the Wilde machine came independent inventions in the same direction from Messrs. G. Farmer of Salem, Massachusetts, Alfred Yarley and Professor Charles Wheatstone of England, and Dr. Siemens of Berlin, and Ladd of America. These inventors conceived and put in practice the great idea of employing the current from an electromagnetic machine to excite its own electric magnet. They were thus termed self-exciting. The idea was that the commutator, an instrument to change the direction, strength or circuit of the current, should be so connected with the coils of the field magnets that all or a part of the current developed in the armature would flow through these coils, so that all permanent magnets might be dispensed with, and the machine used to excite itself or charge its own field magnets without the aid of any outside charging or feeding mechanism. Mr. Z. Graham, of France, a little later than Wilde, made a great improvement. Previously, machines furnished only momentary currents of varying strength and polarity, and these intermittent currents were hard to control without loss in the strength of current and the frequent production of sparks. Graham produced a machine in which, although as in other machines the magnetic field of force was created by a powerful magnet, yet the armature was a ring made of soft iron rods, and surrounded by an endless coil of wire, and made to revolve between the poles of the magnet with great rapidity, producing a constant current in one direction. By Faraday's discovery, when the coil of the closed circuit was moved before the poles of the magnet, the current was carried half the time in one direction and half in the other, constituting what is called an alternating current. Graham employed the commutator to make the current direct instead of alternating. Dynamo-electric machines for practical work of many kinds had now been born and grown to strength. In addition to these and many other electrical machines, this century has discovered several ways by which the electricity developed by such machines may be converted into light. By means of two carbon conductors between which passes a series of intensely brilliant sparks which form a species of flame known as the Voltaic arc, and the heat of which is more intense than that from any other known artificial source. 2. By means of a rod of carbon or kaolin, strip of platinum or iridium, a carbon filament, or other substance placed between two conductors, the resistance opposed by such rod, strip, or filament to the passage of the current being so great, as to develop heat to the point of incandescence, and produce a steady white and pure light. Attempts also have been made to produce illumination by what is called stratified light produced by the electric discharge passing through tubes containing various gases. These tubes are known as Geissler tubes, from their inventor. Still another method is the production of a continuous light from a vibratory movement of carbon electrodes to and from each other, producing a bright flash at each separation, and maintaining the separations at such a rate that the effect of the light produced is continuous. But these additional methods do not appear as yet to be commercially successful. It must not be overlooked that before dynamo-magneto-electric machines were used practically in the production of the electric light for the purposes of illumination, the Voltaic battery was used for the same purpose, but not economically. The first private dwelling house ever lighted in America, or doubtless anywhere else, by electricity, was that of Moses G. Farmer, in Salem, Massachusetts, in the year 1859. A Voltaic battery furnished the current to conducting wires which led to two electric lamps on the mantelpiece of the drawing room, and in which strips of platinum constituted the resisting and lighting medium. A soft, mild, agreeable light was produced, which was more delightful to read or sew by than any artificial light ever before known. Either or both lamps could be lighted by turning a button, and they were maintained for several weeks, but were discontinued for the reason that the cost of maintaining them was much greater than of gas light. It was in connection with the effective dynamo-electric apparatus of M. Graham above referred to that the electric candle invented by M. Paul Jablokoff became soon thereafter extensively employed for electric lighting in Paris, and elsewhere in Europe. This invention, like the great majority of useful inventions, is noted for its simplicity. It consists of two carbon pencils placed side by side and insulated from each other by means of a thin plate of some refractory material which is a non-conductor at ordinary temperatures, but which becomes a conductor, and consequently a light, when fused by the action of a powerful current. Plaster of Paris was found to be the most suitable material for this purpose, and the light produced was soft, mellow, slightly rose-colored, and quite agreeable to the eye. It having been found that carbon was better adapted for lighting purposes than platinum or other metals, by reason of its greater radiating power for equal temperatures, and still greater infusibility at high temperatures, inventors turned their attention to the production of the best carbon lamp. The two pointed pieces of hard conducting carbon used for the separated terminals constitute the Voltaic Arc Light, a light only excelled in intense brilliancy by the sun itself. It is necessary in order to make such a light successful that it should be continuous. But as it is found that both carbons waste away under the consuming action of the intense heat engendered by their resistance to the electric current, and that one electrode, the positive, wastes away twice as fast as the opposite negative electrode, the distance between the points soon becomes too great for the current longer to leap over it, and the light is then extinguished. Many ingenious contrivances have been devised for correcting this trouble, and maintaining a continuously uniform distance between the carbons by giving to them a self-adjusting automatic action. Such an apparatus is called a regulator, and the variety of regulators is very great. The French were among the first to contrive such regulators. Dubosc, Foucault, Serin, Houdin, and Lontin invented most useful forms of such apparatus. Other early inventors were Hart of Scotland, Siemens of Germany, Thomson and Houston of England, and Farmer, Brush, Wallace, Maxim, and Weston and Westinghouse of America. Graham made his armature of iron rods to prevent its destruction by heat. Weston in 1882 improved this method by making the armature of separate and insulated sheets of iron around which the coil is wound. The arc light is adapted for streets and great buildings, etc., but for indoor illumination, when a milder, softer light is desirable, the incandescent light was invented, and this consists of a curved filament of carbon about the size of a coarse horsehair, seated in a bulb of glass from which the air has been exhausted. In exhausted air carbon rods or filaments are not consumed, and so great ingenuity was exercised on that line. Among the early noted inventors of incandescent carbon filament lamps were Edison and Maxim of New York, Swan, and Lane Fox of England. Another problem to be solved arose in the proposed use of arc lamps upon an extended scale, or in series, as in street lighting, wherein the current to all lamps was supplied by a single wire, and where it was found that owing to the unequal consumption of the carbons some were burning well, some poorly, and some going out. It was essential, therefore, to make each lamp independent of the resistance of the main circuit, and of the action of the other lamps, and to have its regulating mechanism governed entirely by the resistance of its own arc. The solution of this difficult problem was the invention by Hefner von Altneck of Germany, and his device came into use wherever throughout the world arc lamps were operated. Westinghouse also improved the direct alternating system of lighting by one wire by the introduction of two conducting wires parallel to each other, and passing an interrupted or alternating current through one, thereby inducing a similar and always an alternating current through the other. Brush adopted a three-wire system, and both obtained a uniform consumption of the carbons. In a volume like this, room exists for mention only of those inventions which burn as beacon lights on the tallest hills, and so we must now pass on to others. Just as Faraday was bringing his long series of experimental researches to a close in 1856-59, and introducing the fruits of his labors into the lighthouses of England, Cyrus W. Field of New York had commenced his trials in the great scheme of an ocean cable to moor the New World alongside the Old, as John Bright expressed it. After crossing the ocean from New York to England 50 times, and baffled often by the ocean, which broke his cables, and by the incredulous public of both hemispheres, who laughed at him, and by electricity, which refused to do his bidding, he at last overcame all obstacles, and in 1866 the cable 2,000 miles in length had been successfully stretched and communication perfected. To employ currents of great power, the cable insulation would have been disintegrated and finally destroyed by heat. Therefore only feeble currents could be used. But across that long distance these currents for many reasons grew still weaker. The inventor, Sir William Thomson, was at hand to provide the remedy. First, by his mirror galvanometer. A needle in the shape of a small magnet, and connected to the current wires, is attached to the back of a small concave mirror having a hole in its center. Opposite the mirror is placed a graduated scale board, having slits through it, and a lighted lamp behind it. The light is thrown through the slits across to the hole at the center of the mirror and upon the needle. The feeblest imaginable current suffices to deflect the needle in one direction, which throws back the little beam of light upon it to the graduated front of the scale. When the current is reversed, the needle and its shadow are deflected in the other direction, and so by a combination of right and left motions, and pauses of the spots of light to represent letters, the message is spelled out. Second, a more expeditious instrument called the Siphon Recorder. In this the galvanometer needle is connected to a fine glass siphon tube conducting ink from a reservoir onto a strip of paper which is drawn under the point of the tube with a uniform motion. The irregular movements given the galvanometer needle by the varying current are clearly delineated on the paper. Or in writing very long cables the point of the siphon may not touch the paper, but the ink by electrical attraction from the paper is ejected from the siphon upon the paper in a succession of fine dots. The irregular lines of dots and dashes were translated into words in accordance with the principles of the Morse telegraph. An instrument was exhibited at the Centennial International Exhibition at Philadelphia in 1876, which was considered by the judges the greatest marvel hitherto achieved by the electric telegraph. Such was the language used both by Professor Joseph Henry and Sir William Thomson, and concurred in by the other eminent judges from America, Germany, France, Austria, and Switzerland. This instrument was the telephone. It embodied, for the practical purpose of transmitting articulate speech to distances, the union of the two great forces, sound and electricity. It consisted of a method and an apparatus. The apparatus or means consisted of an electric battery circuit, a transmitting cone placed at one end of the line into which speech and other vocal sounds were uttered, a diaphragm against which the sounds were projected, an armature secured to or forming a part of the diaphragm, an electromagnet loosely connected to the armature, a wire connecting this magnet with another precisely similar arrangement of magnet, armature, diaphragm, and cone, at the receiving end. When speech was uttered in the transmitter, the sound vibrations were received on the diaphragm, communicated to the electricized armature, from thence by induction to the magnet and the connecting wire current, which, undulating with precisely the same form of sound vibrations, carried them in exactly the same form to the receiving magnet. They were then carried through the receiving armature and reproduced on the receiving diaphragm, with all the same characteristics of pitch, loudness and quality. The inventor was Alexander Graham Bell, by nativity a Scotchman, then a resident of Canada, and finally a citizen of the United States. His father was a teacher of vocal physiology at Edinburgh, and he himself became a teacher of deaf-mutes. This occupation naturally led him to a thorough investigation of the laws of sound. He acknowledged the aid he received from the great work of Helmholtz on the theory of tone. His attention was called to sounds transmitted and reproduced by the electric current, especially by the ease with which telegraph operators read their messages by the duration of the click of their instruments. He knew of the old device of a tightly stretched string or wire between two little boxes. He had read the publication of Professor C.G. Page, of America, in 1837, on the production of galvanic music, in which was described how musical notes were transmitted and reproduced by an interrupted magnetic circuit. He became acquainted with the experimental musical telephonic and acoustic researches of Race, and others of Germany, and those of celebrated scientists in France, especially the phonautograph of Scott, a delicate instrument having a cone membrane and pointer, and used to reproduce on smoked glass the waves of sound. He commenced his experiments with magneto instruments in 1874, continued them in 1875, when he succeeded in reproducing speech, but poorly, owing to his imperfect instruments, and then made out his application, and obtained a patent in the United States in July, 1876. Like all the other remarkable inventions recorded in these pages, this marvel did not spring forth as a sudden creation, but was a slow growth of a plant derived from old ideas, although it blossomed out suddenly one day when audible sounds were accidentally produced upon an apparatus with which he was experimenting. It is impossible here to narrate the tremendous conflict that Bell now encountered to establish his title as first inventor, or to enumerate the multitude of improvements and changes made which go to make up the successful telephone of today. The messages of the voice are carried on the wings of electricity wherever any messages are carried, except under the widest seas, and this difficulty inventors are now seeking to overcome. The story of the marvelous inventions of the century in electricity is a fascinating one, but in length and details it is also marvelous, and we must hasten unwillingly to a close. Numerous applications of it will be mentioned in chapters relating to other arts. In the generation of this mighty force improvements have been made, but those of greatest power still involve the principles discovered by Faraday and Henry 70 years ago. The ideas of Faraday of the lines of force, the magnetic power streaming from the poles of the magnet somewhat as the rays of heat issue on all sides from a hot body, forming the magnetic field, and that a magnet behaves like an electric current, producing an electric wave by its approach to or recession from a coil of wire, joined with Henry's idea of increasing the magnetizing effect by increasing the number of coils around the magnet, enter into all-powerful dynamo-electric machines of today. In them the lines of force must flow around the frame and across the path of the armature, and there must be a set of conductors to cut the lines of force twice in every revolution of the cylinder carrying the armature from which the current is taken. When machines had been produced for generating with some economy powerful currents of electricity, their use for the world's business purposes rapidly increased. Among such applications, and following closely the electric lighting, came the electric railway. A substitute for the slow animal, horse, and for the dangerous, noisy steam horse and its lumbering locomotive and train, was hailed with delight. Inventors came forward with adaptations of all the old systems they could think of for the purpose, and with many new ones. One plan was to adapt the storage battery, that silent chemical monster which carries its own power and its own machine, and place one on each car to actuate a motor connected to the driving wheels. Another plan was to conduct the current from the dynamo machine at its station along the rails on one side of the track to the motor on the car and the return current on the opposite track. Another was to carry the current to the car on a third rail between the track, using both the other rails for the return. Another to use an overhead wire for the current from the dynamo, and connect it with the car by a rod, one end of which had a little wheel or trolley running on the overhead wire, to take up the current, the other end being connected by a wire to the car motor. Another plan to have a trench made leading from the central station underneath the track the whole length of the line, and put into this trench conducting wires from the dynamo, to one of which the car motor should be connected by a trolley rod or brush, extending down through a central slot between the rails of the track to carry the electric supply into the motor. In all these cases a lever was supplied to cut off communication between the conducting wire and the motor, and a brake lever to stop the car. All of these plans have been tried, and some of them are still being tried with many improvements in detail, but not in principle. The first electrical railway was constructed and operated at Berlin in 1879, by Messrs. Siemens and Halske. It was 2,700 feet long and built on the third rail system. This was an experiment but a successful one. It was followed very soon by another line near Berlin for actual traffic, then still another in Saxony. At the Paris Exposition in 1881, Sir William Siemens had in operation a road about 1,600 feet in length, on which it is estimated 95,000 passengers were conveyed in 7 weeks. Then in the next year in London, and then in the following year one in the United States near New York, constructed by Edison. And thus they spread, until every important town and city in the world seems to have its electric plant, and its electric car system, and of course its lighting, telephone and telegraph systems. In 1882 Professor Fleming Jenkin of England invented and has put to use a system called telpherage, by which cars are suspended on an overhead wire which is both the track and electrical conductor. It has been found to be advantageous in the transportation of freight from mines and other places to central stations. With the coming of the electric railway, the slow, much abused horse, the puffing steam engine blowing off smoke and cinders through the streets, the great heavy cars, rails and roadbeds, the dangerous collisions and accidents, have disappeared. The great problems to solve have related to generation, form, distribution and division of the electric current at the dynamos at the central stations for the purposes of running the distant motors and for furnishing independent supplies of light, heat, sound and power. These problems have received the attention of the keenest inventors and electrical engineers, and have been solved. The description of the inventions made by such electrical magicians as Thomas Edison and Nikola Tesla would fill volumes. The original plan of sending but one message over a wire at a time has also been improved, and duplex, quadruplex and multiplex systems have been invented, by Stearns, Farmer, Edison and others, and applied, which have multiplied the capacity of the telegraphs, and by which even the alleged all-talk at the same time habit of certain members of the great human family can be carried on in opposite directions on the same wire at the same time between their gatherings in different cities and without a break. To understand the manner of multiplying messages or signals on the same line, and using apparently the same electric current to perform different operations, the mind must revert to the theory already referred to, that a current of electricity does not consist of a stream of matter flowing like water through a conductor in one direction, but of particles of subtle ether, vibrating or oscillating in waves from and around the conductor which excites them. That the vibration of this line of waves proceeds at the rate of many thousand miles per second, almost with the velocity of waves of light, with which they are so closely related, that this wave current is susceptible of being varied in direction and in strength, according to the impulse given by the initial pressure of the transmitting and exciting instrument, and that some wave currents have power by reason of their form or strength to penetrate or pass others coming from an opposite direction. So that in the multiplex process, for instance, each transmission having a certain direction or strength and its own set of transmitting and receiving instruments, will have power to give its own peculiar and independent signal or message. Apparently there is but one continuous current, but in reality each transmission is separated from the others by an almost inconceivably short interval of time. Among the inventions in the class of telegraphy should also be mentioned the dial and the printing systems. Ever since the electric telegraph was invented, attempts have been made to use the electric influence to operate either a pointer to point out the letters of the message sent on a dial, or to print them on a moving strip of paper, and also to automatically reproduce on paper the handwriting of the sender or writer of the message. The earliest efforts were by Cooke and Professor Wheatstone of London, in 1836–37. But it was not until 1839, after Professor Henry had succeeded in perfecting the electromagnet, that dial and printing telegraphs were successfully produced. Dial telegraphs consist of the combination with magnets, armatures and printed dial plate of a clockwork and a pointer, means to set the pointer at the communicating end, which in some instances has been a piano keyboard, to any letter, the current operating automatically to indicate the same letters at the receiving end. These instruments have been modified and improved by Briquet and Froment of France, Dr. Siemens and Kramer, and Siemens and Halske of Germany, Professor Wheatstone of England, Chester and Hamblet of America, and others. They have been used extensively upon private and municipal lines both in Europe and the United States. The type printing telegraph was coeval with the dial, and originated with Morse and Vail as early as 1837. The printing of the characters is effected in various ways, sometimes by clockwork mechanism, and sometimes by the direct action of an electromagnet. Wheatstone exhibited one in 1841. House of Vermont invented in 1845 to 1846 the first printing telegraph that was brought into any extensive use in the United States. Then followed that of David E. Hughes of Kentucky in 1855, aided by his co-inventor George M. Phelps of Troy, New York, and which was subsequently adopted by the French government, by the United Kingdom Telegraph Company of Great Britain, and by the American Telegraph Company in the United States. The system was subsequently greatly improved by Hughes and others. Alexander Bain of Edinburgh in 1845-46 originated the modern automatic chemical telegraph. In this system a kind of punch was used to perforate 2 rows of holes grouped to represent letters on a strip of paper conducted over a metal cylinder and arranged so as to permit spring levers to drop through the perforations and touch the cylinder, thus forming an electrical contact, and a recording apparatus consisting of a strip of paper carried through a chemical solution of an acid and potash and over a metal roller, and underneath 1 or 2 styles, or pens, which pens were connected by live wires with the poles of 2 batteries at the sending station. The operation is such that colored marks upon the paper were made by the pens corresponding precisely to the perforations in the strip at the sending station. Siemens, Wheatstone and others also improved this system, but none of these systems have as yet replaced or equaled in extensive use the Morse key and sounder system, and its great acoustic advantage of reading the messages by the click of the instrument. The type printing system, however, has been recently greatly improved by the inventions of Howe, C. L. Buckingham, Fisk and others in the United States. Special contrivances and adaptations of the telegraph for printing stock reports and for transmitting fire alarm, police, and emergency calls, have been invented. The erection of tall office and other buildings, some to the height of more than 20 stories, made practicable by the invention of the elevator system, has in turn brought out most ingenious devices for operating and controlling the elevators to ensure safety and at the same time produce economy in the motive power. The utility of the telephone has been greatly increased by the inventions of Hughes and Edison of the microphone. This consists, in one form, of pieces of carbon in loose contact placed in the circuit of a telephone. The very slightest vibrations communicated to the wood are heard distinctly in the telephone. By these inventions and certain improvements not only every sound and note of an opera or concert has been carried to distant places, but the slightest whispers, the minute movements of a watch, even the tread of a fly, and the pressure of a finger, have been rendered audible. By the aid of the electric current certain rays of light directed upon the mineral selenium, and some other substances, have been discovered to emit musical sounds. So wonderful and mysterious appear these communications along the electric wire that each and every force in the universe seems to have a voice awaiting utterance to man. The hope is indulged that by some such means we may indeed yet receive the touch of a vanished hand and the sound of a voice that is still. In 1879 that eminent English scientist, Professor William Crookes, published his extensive researches in electrical discharges as manifested in glass tubes from which the air had been exhausted. These same tubes have already been referred to as Geissler tubes, from the name of a young artist of Bonn who invented them. In these tubes are enclosed various gases through which the sparks from an induction coil can be passed by means of platinum electrodes fused into the glass, and on the passage of the current a soft and delicately tinted light is produced which streams through the tube from pole to pole. In 1895, William Conrad Röntgen, professor of physics in the Royal University of Würzburg, while experimenting with these Crookes and Geissler tubes, discovered with one of them, which he had covered with a sort of black cardboard, that the rays emanating from the same and impinging on certain objects would render them self-luminous, or fluorescent, and on further investigation that such rays, unlike the rays of sunlight, were not deflected, refracted or condensed, but that they proceeded in straight lines from the point at which they were produced, and penetrated various articles, such as flesh, blood, and muscle, and thicknesses of paper, cloth and leather, and other substances which are opaque to ordinary light, and that thus while penetrating such objects and rendering them luminous, if a portion of the same were of a character too dense to admit of the penetration, the dark shadow of such obstacle would appear in the otherwise luminous mass. Unable to explain the nature or cause of this wonderful revelation, Röntgen gave to the light an algebraic name for the unknown, the X-rays. This wonderful discovery, at first regarded as a figment of scientific magic, soon attracted profound attention. At first the experiments were confined to the gratification of curiosity. The interior of the hand was explored, and on one occasion the little mummified hand of an Egyptian princess folded in death 3,000 or 4,000 years ago, was held up to this light, and the bones, dried blood, and muscle of the ancient pharaohs exhibited to the startled eyes of the present generation. But soon surgery and medicine took advantage of the unknown rays for practical purposes. The location of previously unreachable bullets, and the condition of internal injuries, were determined, the cause of concealed disease was traced, the living brain explored, and the pulsations of the living heart were witnessed. Retardation of the strength of the electric current by the inductive influence of neighboring wires and earth currents, together with the theory that the electric energy pervades all space and matter, gave rise to the idea that if the energy once established could be set in motion at such point above the ordinary surface of the earth as would free this upper current from all inductive disturbance, impulses of such power might be conveyed from one high point and communicated to another as to produce signals without the use of a conducting wire, retaining only the usual batteries and the earth connection. On July 30, 1872, Mahlon Loomis of Washington, D.C., took out a patent for the utilization of natural electricity from elevated points for telegraphic purposes, based on the principle mentioned, and made successful experiments on the Blue Ridge Mountains in Virginia near Washington, accounts of which were published in Washington papers at the time. But being poor and receiving no aid or encouragement, he was compelled to give it up. Marconi of Italy has been more successful in this direction, and has sent electric messages and signals from high stations over the English Channel from the shores of France to England. So that now wireless telegraphy is an established fact. It is certainly thrilling to realize that there is a mysterious, silent, invisible and powerful mechanical agent on every side of us, waiting to do our bidding, and to lend a hand in every field of human labor, and yet unable to be so used without excitement to action and direction in its course by some master, intermediate between itself and man. The principal masters for this purpose are steam and water power. A small portion of the power of the resistless Niagara has been taken, diverted to turn the machinery which excites electricity to action, and this energy in turn employed to operate a multitude of the most powerful motors and machines of many descriptions. So great is the might of this willing agent that at a single turn of the hand of man it rushes forth to do work for him far exceeding in wonder and extent any labor of the gods of mythological renown.